Okay, good morning again. Before I start, I have one question for you. Have you ever touched auto-scale button on your oscilloscope intentionally because you didn't know what you measure? What's the range? What do you measure? Okay, that's fine. I expected this because it's a shame if you don't know what you measure. But honestly, at the end of this presentation, you will see that sometimes in our company, we hope we have this button and we can touch it and have some device which can find the range of those stuff we measure, we do. Sometimes it's so complicated because as you can see on the title of the presentation, it's a high-end device. That means that no one did it before us. So we are the first. And so that's why it's somehow challenging, even in manufacturing. It's even in development. My name is Kříž, and I'm responsible for hardware development and tool development at BTL Medical Technologies company. Let's go. By the way, this title was done by ChatGPT. That's just a funny fact because my previous title, or that what I made up, was, I don't know, boring. So this is pure artificial intelligence. So let's say a few words about our company so you have context. It will be really quick. So it's a Czech company. This year we celebrate 30 years. For me, it's really important. It's a Czech company, has a Czech owner, Czech headquarters, not far away from here, like 2 miles away on Evropská Street. Nowadays, we have 350 R&D engineers and 3,500 people worldwide. What we do, basically non-invasive stuff for medical. That means we don't go under the skin. Usually, those devices we do, they help people to regenerate themselves. You will see. And one more thing, 95%, that's my guess, we don't have statistic for that, we do in-house. Previously, we had a problem with tier 1 manufacturers for automotive. They didn't deliver it to us. So we found out that it's better to do everything in-house. That means all the plastics, all the PCBs, basically all the stuff. So we have all stuff, so we can do whole design, whole device. We can manufacture all the device in-house. Good. Something about our devices we design. It will be quick go through just for motivation, so I can speak about the challenges in manufacturing. So the first one is the typical, our devices, they are in such a box, white box. This one particularly do some magnetic stimulation. So basically, sorry. There's a pointer. Perfect, doesn't work good. So this is the device itself. It has some kind of applicator. And this one particularly do 2 Tesla's pulses. And it helps with chronic pain, for example, some muscle relief. So it's a big magnetic field. So it means we should shoot to the applicator with 1.5 kilovolts, 1,000 amps in 250 microseconds. So it's a massive energy we deal with. Second device, that's my favorite one. Again, high voltage, 10 kilovolts, 500 amperes in 250 microseconds. In the applicator, you can see here, there is some piezo element. We shoot this energy to this piezo element, and it does mechanical pressure wave, and it works literally under skin. So somewhere before I said that it doesn't work like under skin, but it's not needle. It's It's just the applicator on your skin, and the pressure is applied and works below. Basically, it helps to activate some rehealing process in the damaged tissues. Other device, basically, this is microwave oven, but for human body. So it does 300 watts at 27 megahertz. So completely different technology, no magnetic. This is RF. Again, helps with pain relief, some problems with joints, for example. And bam, other device, ECG, something which measures your heartbeat, and it's from signals they are 0.5 millivolts to 5 millivolts. So something totally different. It's battery powered. It's not big device. So this was simply our portfolio. If I go forward, you see another devices. So there's plenty of them. So what are those manufacturing challenges? For the answer, we have to jump to our production. Actually, we have two productions. One is near Prague, 30 kilometers away in town Benešov, where they do PCB assembly only. There is a second one in Bulgaria. I will be talking about that soon. In our portfolio right now, we have like 40 to 50 totally different devices. That's the first challenge, to develop them and have them in the portfolio. For the PCB assembly, if you have 50 different devices, each device compounds from, I don't know, 5 to 10 PCBs. It makes like 400 different various designs. But since it's a high-end, as I said at the beginning, that means we don't produce much. The devices, they are expensive, so we don't sell many devices. So we have small batches in the production, just 100 pieces. This is, again, big challenge, because if you are automotive, you have many PCBs, you do line, and you're fine with it. But we have to switch the lines, SMT lines, you can see here. Okay, still. Or manual THD assembly, really often. That's challenging. If we see assembly process over here, if you do SMT assembly, there is a rejection rate about 2%. It's pretty high, but if you see 400 different designs, it's kind of fair or right, because the machine has to be switched really often, so you cannot tune up all processes. In the process behind the SMT line, there is automatic optical inspection, which you can see here, the output. Basically, it's a 3D scanner which scans all PCB, find out whether all parts they are assembled properly. So after this stage, we are pretty fine with the PCB. There is no mistakes or failures. But then we have some kind of manual THD assembly, and that's the big problem. We don't do consumer electronics, so you saw big devices, big powers, we need big components. That means big capacitors, big transducers, and stuff like that. So the PCBs, they are big like this. And the stuff cannot be assembled by SMT line. It has to be still done by human. And people, they do mistakes. So after they put it together, there is some kind of soldering, solder wave, or selective soldering, or manual soldering. And then what? We have, you can see over here, again, 3% of rejection rate. That means after SMT, 3% of PCBs. That's average number. There are some PCBs where we have like, I don't know, 1% or below 1%. Some designs, they have 10%, which is really bad. So if we do basic math over here, so if our device composed from 10 PCBs, and we have 97% chance that the PCB is all right, after all, there's like 27% chance that the device will not turn on, or if it turns on, there will be some kind of problem, which it mustn't. So what we do? 10 years back, it looked like this. Basically, there was a man who was measuring PCB. Well, it was fine, because 10 years back, we did a small amount of PCBs. Basically, guy measured with a scope, with a multimeter, and the press had some kind of prescription. It's all on the screen over there, and it takes 15 minutes each PCB, which is kind of long time. So that was a challenge to change this. Problem, it's not safe. Still, there are some live parts. The guy who checked the PCB can be harmed somehow. It's repetitive work. People did mistakes, so they sometimes didn't catch the failure board. This is another option. You don't measure each PCB separately, but basically you get the whole device, you put it on some kind of wooden desk, and you just remove one of those PCBs and put there that one you want to check. That's another approach we didn't do anymore, or we don't do anymore. Still, there are some relics. That's another challenge. If you put something on your production, no one wants to change it in the future. So basically, what you put there, it would live there forever, basically. And we have still devices after 25 years, and we can sell them. We don't sell them in Europe or in America, but in Africa or Asia, people still buy it because they are like some kind of high-end and can beat competitors. So if you do it like wrong way, like this, it can be still in the production. That's challenging for them right now. One thing I didn't say, nowadays we do 3.5 of 350,000 PCBs a year. That means 2,000 PCBs per day. That's a massive number. So this approach doesn't work anymore for us. So what we can do? Last year we bought this machine. Perhaps you think that's the resolution, or I can say that it's a resolution, but honestly not. This is Flight Probe Tester. So big machine. It's big like car, something like this. And there is about 6 needles, or that one we have has 6 needles, which checks basically all components on the design, each one, each capacitor, each component. It does really quickly. It can be tested within 2 minutes. What's another benefit? The implementation costs only 2 days. So basically, if you have PCB in 2 days, it can be tested. So that's perfect. But there are some kind of disadvantages. These machines, they are done for automotive or some consumer electronics. So they have limitations in voltage. They can measure up to 100 volts, 3 amps. And as you saw, the devices at the beginning, they have like 1.5 kilovolts, 10 kilovolts, and stuff like that. So that's a problem. Another limitation is functional tests. Here you can check all the components on the PCB, but you cannot start the PCB itself. There can be a lot of functions, some safety features, but you cannot check them unless you start the device itself. So this is a solution. It really helps. It's really expensive. It costs like 40K euros. It's a kind of future, but still we must do this, which is PCB fixture or some custom PCB tester, bed of nails, depends how you call it. It's perfect thing. It's reliable. You just put the operator puts PCB inside this machine. There is a program behind which has to be developed, programmed. It's based on LabVIEW, but it can be programmed anyhow. It can test things up to 10 kilovolts, depend what you design inside. Basically, there are some kind of needles beneath the PCBs. You can see over there. Operator closes, and it's testing. It's testing. That's pretty easy for everyone. It's safe, and it takes, I don't know, 5 minutes, 3 minutes. It's pretty fast. The disadvantage is it's really expensive. The development of this costs 4 to 6 months of manwork, which we can translate into the 30,000 euros, which is pretty expensive, but we have no other chance, or if we want to test something really powerful. So this is massive challenge for us. Do these things, because if you do this kind of tester, the guy doesn't do development of new device we can sell on the market. Basically, this is thing we have in the production, and it pays only for checking whether there is problem or not. So if I summarize this section of production, the challenge is small batches, big variety of PCBs, high voltage, different technologies, ultrasound, big currents, RF. All these stuff has to be measured somehow. So we mustn't send anything to the final device assembly which doesn't work. If we do that, it's a big, massive problem. It costs money because you have to, after all, dismantle the whole device in the production just before you want to send it to the customer. So this we want to avoid. Some kind of future where I see the future or how to handle this challenge is this stuff, some kind of rack device. We still use this kind of fixture, but there will be no electronics inside. On previous slide, we could see, come on, there's a 5 or 6 PCBs inside the fixture. That's a massive development. Over there would be just wires between this big rack, and in the rack there will be powerful machines. So I expect the design should be developed like within a month, not in 6 months. So that can be future. The problem is that you have to really need to know what you want to measure after all. And I can say after 6 years of having fixtures or that flying probe tester, we know what we want. So hopefully next year we will finish this project and it will be better and no challenge. But we'll see. So have we won? Have we won if we test all PCBs? Not at all. The PCBs goes to the second production, Bulgaria, Plovdiv. It's, let's say, Brno in Bulgaria, Plovdiv, nice city. It takes 2 days for truck to go there. All PCBs there are right. So if they put everything together, we have such a device. You can see there is a lot of PCBs, not only PCBs, but other stuff. Mechanical parts. We put it together. Will this work? I don't know. Likely yes, but still we are not sure. And we have some medical standard, 6601. It says that all medical devices must meet this standard, and all devices has to be safe and effective. Basically, it means that if you have a microwave device which does RF, and it should do in the manual like 300 watts, you should be sure that it does 300 watts. If you have magnet or that SIS system with magnetic field, 2 Teslas, you need to prove that it does 2 Teslas. Each particular machine does it. So that's kind of different from consumer electronics. We need to check each device for effectiveness and for safety. That means leakage currents. All that procedure all that procedure takes more than 30 minutes, up to hour. So every single device we produce, we have to check for that long time. So for the supermagnetic inductive system, which you saw at the beginning, that's this one. The final inspection procedure looked like this. So basically, you have some trolley over there, and some kind of this stuff, which is the yellow one, and you measure magnetic field. That's over here is magnetic sensor. That's kind of easy stuff. But if you have RF, there's not just magnetic field, but RF 30 watts. That's microwave heating for the tissues. It's much more difficult. So that was the easier one. And there's the favorite one of mine. That's focused shockwave. I showed you at the beginning that that device which does a massive pressure under your skin. Okay, where it is? Over here. See, there is some kind of lens, piezo element, and the focal point is like, I don't know, 5 centimeters below your skin. It does 65 megapascals. So if we calculate a bit, it means 6.5 kilograms per square millimeter. So it's a massive bump into your body, and something we have to measure before we leave this, before this device leaves our production, and we have to be sure that it works fine. And we have massive problems with this lens. Like 50% of lens, if we assemble them, they don't work basically because the batches they are small, so they do it manually. They cannot use the robot. That's the challenge. So how we approach? The measurement looks like this. It's basically applicator beneath some barrel with water, and we put there PVDF sensor. That was in the beginning, our first try. PVDF sensor is basically piezo element which does some energy, voltage, and some amps. You amplify it and you see what's going on in the water if you meet the focal point and other things. This was for our first try, 200 euros bank. We saw some signal, but after all, we definitely didn't see what we expected from simulations. That was a massive problem. And that's what I was talking about at the beginning. We don't have anything like auto scale we can touch and find out what's going on there. So our second approach was mill plate hydrophone, which looks pretty similar to this. Basically, both devices, PVDF and mill plate one, look same. It's a kind of needle which you put into the water, and you expect something like this. But we didn't see this curve before. We had some kind of simulations before. So with this Miller plate, hydrophone for 2 kilo euros, we did a measurement, but it survived only 10 shoots of this device. Good. Right now, we at least know what's going on in the water, and it's pretty painful because it's completely unlinear. With these pressures in the water, water doesn't behave like you expect, like, I don't know, Newton liquid. It works kind of different. So we at least know that we have this kind of pressure, because at the beginning of development, we know it works. This device works fine. It destroyed, or not destroyed, it harmed our colleague finger. So it did anything, but we didn't know how does it work. So how we sort it out in the production? I'm talking about final inspection. This works for development. You can destroy, I don't know, 10 pieces of this Miller plate stuff. It costs money, but you cannot use it for every single piece. So final solution was this. We bought a fiber optic hydrophone, which is really, really interesting thing. It cost 40 40 kilo euros. It's really expensive. Only 2 laboratories in the world does this, if I know. And it's not that precise, but it works for us. How does it work? Basically, if we shoot by applicator to the water, imagine that there is an applicator. There is a pressure wave. This goes to the next to the fiber, and the magic is that there is some kind of refractive index. There is a laser beam inside the device. I think the device is over here, and you shoot the laser into the water by the fiber. And at the end of the fiber, there is some kind of refractive index between water and the fiber. Normally, you see on the scope nothing. But if you shoot the pressure in the water, as I said, the water is not linear with this pressure. You can see different refractive index at the tip of the fiber. So you see basically by optics the pressure in the water, which is amazing stuff, I would say. And no one did this before us, only these 2 laboratories. And they didn't have any experience with that. They didn't have machine it could do some kind of pressure. So kind of we was most experienced in the world that time with this experiment. We did this 5 years back. Nowadays it's perhaps different. But it's suitable for final inspection, this kind of thing. It costs many thousands euros. Actually, it's not. But nowadays we know how does it work. We can measure it perfectly. So we can use really simple stuff for our final inspection tool, which is this. This is like, again, PVDF sensor, but this one, the original purpose is for washing machine. Basically, it measures the bumping of washing machine. So simple sensor, we shoot into this stuff, which is final inspection tool, but just 10% of the total power of the device itself. We have some kind of table where we can compare the results of this tool with the previous one, with the fiber optics, where we could measure up to 100% of power we can do with the device. And that was our approach, and it works fine. So we are happy, but it cost almost 1 year of development, and we had to buy a lot of devices, many experience. So if I sum it up, the first message is even inter-operational test of PCB can be challenging for us, since you don't do some customer electronics or what Foxconn does. That means iPhones, where you do series about 1 million pieces. And the second message is that sometimes you have to develop another device if you want to measure the effectiveness of the previous one. And it costs a lot of effort, but you have to do it if you want to be sure that it works fine. You just cannot throw the device on the market and hope that it works fine. So that's it. I hope you enjoyed that. I hope I give you some motivation or message. It wasn't really deep. I didn't go deeply in any sensor. I hope you enjoyed that. And now you know that in medical devices or in this branch, it can be challenging. And hopefully we see you soon.
Thank you.
Cheers.
Thank you, Jan, for your interesting presentation. And now it's time for questions. So is there any questions?
Oh, my.
Just wait for the mics.
Okay, ask me.
Okay, so Thank you for your presentation, and I would like to ask you about certification of electronics in medical area, because I am working in aerospace, and the certification is very long process with some specific rules, some standards, and so on. It takes from 2 up to 5, 7 years. So, do you have some idea how the electronics in medical area is certified, and something about the process? Do you have some info about it?
Well, that's a great question. As you said, it's a long process, and we wait for it up to 1 or 2 years. And basically, we do the certification during our development, or we try to do that. For it pays the standard 60601, so we need some CE certification, CB certification, and stuff like that. We sell the devices around the world, like, I don't know, 80 countries, so we must fulfill different standards. But basically, we go for this authority to have this standard like 1 or 2 years before we release the product. That's how we approach it. We send it the device, we know how it works, how it should look like at the end, but the device is not complete stuff. So we don't wait until the device is completed, final. So we do it previously. And we have 7 different authorities, because in our branch it's difficult to find. It's not like you go for shopping and you enter the shop and say, hey, do certification for my device. And it's different. You wait for 2 hours, 2 years. So it's complex things. We try to do the things in advance. That's the thing, how we can handle it. And we have big experience. We know what they want to see. And we have 200 people which does this thing, RA, department, regulatory. So experience, and we do it in advance. So was it the answer?
Yes, thank you.
Okay.
Another question from Professor
I was rather surprised, but maybe it was my mistake, that you are using 25 megahertz for heating.
Was there 25?
Yeah. Was it really 25 megahertz?
Oh, sorry. That was my mistake. It was 27 gigahertz. So,
27 gigahertz.
Yes, it was typo. That would be.
Any more questions?
That wouldn't work. Yeah, we need to meet the free bandwidth, basically.
Okay, actually, I have one question. You said lots about testing of the electronics and the process about it. But what about the testing on humans? Because you are the leading company which develops the instruments which interact with the human body. And you are a worldwide leader, I can say. How do you feel, or how do you know what the market wants? Do you cooperate with some physiotherapists, or with some hospitals, or some medical staff? How to, or what to do? And if so, how do you test it with the humans, if I can ask on it?
Yeah, not easy question. Where to start? Definitely, we want to be sure before we sell the product that it doesn't harm patient. So if it's something what is already on the market, we usually have some kind of precedence, so we can use this experiments, and we can say that the technology is similar, but higher frequencies, high power, and stuff like that. That's the easier one, but still we have to try it on I don't know, like dead flesh, basically. So we apply it on the meat, and we see if we don't burn the skin and stuff like that. Then we try it on people. Definitely there is a stuff I cannot say in English. I'm not sure the word, but it takes, I don't know, 3 months to 1 year of experiments with people, with doctors, with clinics, and some papers rise up with this. So that's one thing. If the technology is already in the market, if it's something really, really new, which was the magnetic one, magnetic one device, then yes, it's pretty similar, and it's not an easy question, and I'm not a product specialist.
Okay. And do you have also some feedback from doctors, for example, how to improve the sensors or some specific parts of the instruments? Do you also cooperate? Like, do you continuing on development of?
Yeah, definitely. We must do that. Yeah. We must, by the standard, we must collect feedback, all things that someone was harmed by this. And this happens because all these devices, they are like on the border between it helps and it hurts. All medical devices, it's written in the standard. It should harm people, but after all, it should heal somehow. So, for example, 2 months back, I tried, it's the device called fraction therapy, which is like 100 needles. They go beyond or beneath your skin, actually. They are on the applicator. It goes like this into your skin, and some RF current is applied to irritate the cells in your skin and start some healing procedure. And it was really painful. I was harmed, like it was like be 1 day on this direct sun. But after all, it worked. So yeah, in our company you can try it, and I tried this device before we sell it on the market. So I was a part of this stuff. About the feedback, yes, we have to collect it, and doctors, they say, hey, this didn't work. Sometimes we find out new feature. We say, hey, this is pretty nice, but doctors, they say, I don't want it. So yeah, it's a regular process. The doctors, they are customers for us. We need to hear them, hear their voice.
Okay, thank you. So any more questions, please?
You mean the previous device with the pressure one? I think with this device it is like ting 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 ting. So this currency. The magnetic one is like 100 hertz. This is slower, like I don't know, 50, 40 hertz. So it can be really fast. Cheers.
Okay, I have a question. You said that you are a Czech company and you are producing everything in Czech Republic or at least at Europe, and which is not a standard, I would say. And I would like to ask you, what is the reason why you are not producing in China? Is it quality or intellectual property protection?
Some things actually might be produced in China. It was plastics or molds, but we collect them and we have them in the Benešov. It's reliability. That's the thing. We cannot, as we saw, we don't produce so many machines, so they don't want to produce for us. If we order something, we cannot trust them that they deliver in the time. Right now, we have on our stocks things for 2 years in advance. So basically, if anyone sell us anything, we can be alive for 2 years. That's the strategy. And why we do everything in-house? Because everything is under our control. We can control the processes, and sometimes we are not good. All the processes, they are under the development, so we want to have them on our eyes, and have it under control. But I'm not the one who should choose this way, how we do it. But basically, I'm happy that we can do this approach. We don't send everything to China, to other states, other countries. Yes, it's expensive, but as we do high-end things, it can be more expensive. Doctors, they sell big money for that, so we can afford this. We can do it in-house, have everything under our control. So that's the answer. But it's not ideal world. Like ideal world is put everything ever.
Okay, thank you.
Okay, any more questions?
Yeah.
No, it's not okay.
Go ahead.
Like people here and they have to hear you.
You said it. You have stock for 2 years, right?
Yeah.
And that's quite expensive also to keep it on stock. Has it changed over, let's say, the couple of last years during the COVID time when there were the delinquencies, or did you from the beginning plan to have, let's say, this kind of stock at your hand?
Good question. Yeah, it's like that. It was because COVID. Previously, we had like bigger stock amounts, but nowadays we have even bigger, since like we have to sell. We have to be sure that if someone orders our device next week, he will have it in the clinic. So that's another challenge I didn't say. We have push production rather than pull. So it doesn't mean that someone orders the product and we start to do assembly. It's different. We push it. So we have some kind of forecast expectations, how many we will sell, and we produce in advance. So the customer can have this device within days. So that's our strategy, to have it soon. If you buy something really expensive, you want to have it right away. It's like Apple.
Okay,
and yes, it was COVID, basically. It's massive amount of things, like Wolf Benešov is basically our stocks of things, and it's true. This is interesting topic for another presentation, how we stock things and how we handle this. Good question, thank you.